Hello everyone and welcome to our PowerPoint presentation for the midterm assignment. We are group 3, we are Elias Hammer and Katharina Stracke. So this is our first molecule and here is the retrosynthesis for it. And when we look at it and if we know what we are looking for, we can see that it's a good decision to first cleave those two bonds here, so that this is formed via a ring forming reaction, to be more specific, a Diels-Alder reaction, because this part of the molecule basically looks exactly like a really good dienophile with an alkylene with two electron withdrawing groups. So if we go one retrosynthetic step back, we can see our two synthons, but this actually doesn't make too much sense because the charges don't mean too much. So I think it's a better idea to just go back to the reagents, and here we can see the two molecules, and this for me it looks like a pretty standard Diels-Alder reaction to form this molecule. The mechanism is this attacks here, this attacks here, and this double bond goes here. So it's actually pretty standard, and this is already one starting molecule here. The other molecule is this, and in the assignment there was the hint that we can use, or we need to use, cyclohexanone as starting material. So now it's all about transforming this back into cyclohexanone. And when you look at this double bond, we can form that by dehydration. And so if we go one step back, we have this molecule, and this is like a tertiary alcohol, like an alcohol. And this is easily formed via a Grignard reaction, and then we are by the starting material again. So, and the forward synthesis is pretty, like, if you know all this, it's pretty forward. And from this starting material, we just do a Grignard reaction. We found this in this exact reaction in this paper here, with 70% yield. Then we found this dehydration reaction, the exact same one, in this Brazilian paper here with 80% yield. And then it's only about the Diels-Alder reaction. And this is not the exact same reaction that is in this paper we provide here, but it's close enough, I think. The only difference is, if I remember correctly, that there is like a methyl group or two, and this is a very good yield, this step in 95% yield. So this is our idea how we would synthesize this molecule. And yeah, so much to the first molecule. So here we can see our second molecule, and down here we can see the retrosynthesis for it. So the first step is just a functional group interconversion, because we thought we can add this part of the molecule more easily via an epoxide and then change it into a bromide in the last reaction step. So the second last step is the removal of the protection group, because both of the alcohol, the aromatic one and this one, are protected during the reaction to prevent interference. So now we are at the first interesting reaction step, and we decided to form this ring on top of this ring via an Robinson annulation. So a Robinson annulation is a Michael addition followed by an aldol reaction. So if we think backwards, the aldol reaction comes first here in the retrosynthesis. So this bond here is formed via the aldol reaction. So this gets annulated and attacks here. It's called condensation because the carbonyl group gets separated from the molecule in form of water. And this bond here is formed via an Michael addition. So this gets annulated here and attacks this Michael acceptor, this alpha beta unsaturated carbonyl molecule here. So this is the Michael addition, and then it's the aldol conversation, and again this whole reaction is called a Robinson annulation. The next step is just to add a protection group, because we thought the alcohol here needs to be protected so it cannot react with the alpha beta unsaturated carbonyl over here, and it doesn't bother during the Robinson annulation. So now we are here, and this part of the molecule is, like I said before, added with an annulation reaction of an epoxide. So those are the synthons, and this is the epoxide, and this is this compound which gets annulated over here and attacks the epoxide. And the last retrosynthetic, or rather the first step in the reaction, is to protect this alcohol so that this does nothing during the whole reaction, and it gets the protection group gets removed in one of the last steps. So that's for the retrosynthesis, and the forward synthesis is here. So we start with this molecule, we protect it with TMS. We decided to go with TMS because it can be cleaved very easily, and it's also pretty stable against bases, and we have no acidic reactions until the end, and there are two basic reactions. So the next step is the annulation, and we actually thought about annulating this molecule with an enamine first, so to transform this via an enamine-Stokes reaction into an enamine, because it would enolate more easily this way. But of course it would be an extra reaction step, so we ultimately decided against it. And we also found a paper for this carbonyl annulation with an epoxide. That's this paper here, which they used quite different molecules, but the reaction worked in a very good yield, so that's why we think this is the best way actually. Then the next step is to protect the other alcohol. Then when both alcohols are protected, we can do our Robinson annulation. We actually found a paper which used a very similar molecule. It's nearly the exact same molecule, but it doesn't have the alcohol here and the chlorine here, and the reaction was done in a 37% yield. So then after we are here, we just have to remove the protection groups. That can be done with acetic acid, and then we have to transform the alcohol into a bromine, and then we are at our target molecule. So that's our synthesis. Yeah.